Welcome back to Math 210 Calculus 1. So this day is well, it's the last day of class, which is great. That always has, I hope, a celebratory feel in there somewhere, even though I know there's anxiety for the final exams as well. Uh, when I'm planning out the syllabus, I always try to block out one or two free days in case of snowstorms, uh, emergencies, things like that. And we kind of land with, in this case, one free day, which is today. So we've gone through exactly what we meant to. We've gone through the first 5 chapters. We've got nothing else to do. Um, so this can certainly be a review day, or it can be a short day where I end class early, but also hang out and answer any questions. I'm a little tightly scheduled this week, so we can also use this class time for me to like create some review exercises for you. Um, Anything that's going to make you feel confident and comfortable going into that final exam, which is really just what, 49 hours from now, this Friday at noon. So you know when I was a younger teacher, I would kind of spend the review day just kind of doing problems on the board, and it's not clear to me how much that actually helps you. Although, like if you have a problem you want to see, I'll definitely do it. Like that's different. Like if you request something, I'll definitely do it. But initially, why don't I just turn it over to you and using your voice or typing into the chat. Is there anything you'd like to see me do? Is there anything you'd like to talk about? Is there anything you'd like from me before the final exam that I can maybe do right now? Yeah, so what's the final exam going to look like? What I'll try to do is, our tests are meant to be 55 minutes, and I usually make them 5 questions on average, and I feel like the final exam should be, well, that's like a 2-hour test, so it'll be like 10 questions, like 8 to 10 questions on average, and it'll be designed to do in just under 2 hours with a little bit of extra time to get that done. And in fact, I suppose that, like, would you like to see a previous exam, like a previous final exam? Maybe I can do that. Maybe I can do that for you. And like you've seen, like my previous, test one from 2016, and it was, similar but a little bit different. So it's not like this. Like if I give you a my final exam from like 5 years ago, I'm not promising it'll be, just the same, but maybe that can be helpful. Oh, let me actually. I've found some other information too that I can give to you. Another question came in. Can you post solutions for exam 3 on Google Classroom? Yeah, I haven't posted those yet. I can definitely get those to you. I have to, I can't do that right now because I have to like, you know, do them. But I'll do that for you. Let me post some other stuff right now. So let's see. How can I do this? I just put a document in the chat, and this was my review for the final exam in fall 2016. So I put the, oh, let me put it for everybody. I sent it to one person by accident. And I put this in with a little bit of trepidation because there's some dates on it that are out of date. Obviously, our exam is not on December 16th, so you know you can ignore that stuff, but you can pay attention to the topics. And the review questions, this is from the previous edition, so like I can't. They're probably pretty stable, although the page numbers might change a little bit. So those, you know, some of those review questions might be a little bit out of date, but the topics list is not going to change. So if that's helpful for you to just have, I mean, it's just going through what we did, you know, first 5 chapters of the book. Like, I trust all of you can do that too, but if it helps to have that topics list there, you're welcome to it. And then let me find the actual final exam, and I'll put this on the classroom. Yeah, let's check this out together. I won't put the other one on the classroom because I don't want to put things on the official classroom that have dates that are incorrect. Okay, so that's actually posted for you now. So if you go up to our Google Classroom and go to the stream, you know, the first thing you'll see is 11:22 a.m. new material posted, final exam from fall 2016. Should be able to click on that, and I'll share it. I'll share my screen and show it to you as well. What am I sharing? Okay, sorry about that. All right. Okay. And Zoom is just complaining at me that it thinks a window is over this, but there isn't one. So bear with me. All right. Okay, so hopefully that's better. Um, no books, calculators, cell phones, or iPods allowed. So you could tell this is a little bit old. Um, got some formulas, derivative, linear approximation. Double angle, logarithm, right hand, left hand approximation, a couple formulas for some of the first whatever numbers. A couple angles for looks like sine 30 and cosine 30, sine and cosine of 60. And so, yeah, this is what you'll see. Calculated derivative. Now switching to Leibniz notation. This is asking about implicit differentiation. You see me switching up the notation each time. Calculate the derivative of this function with respect to t, just the quotient rule there. Two derivatives of x times sine x. So first problem, we're practicing derivatives. Second problem is a little word problem with this exponential function. How long will it take the population to double? I mean, we didn't do stuff exactly like this, but like you don't necessarily need someone to have already explained it to you, right? Like the initial population is 1,000, so you're solving the equation 2,000 equals 1,000 times e to the t over 5. So this is kind of like a pre-calculus problem where you're solving for t. And then yeah, linear approximation. So like actually this is kind of a cool application of linear approximation for like a real world setup. Don't mind that. So find the signed area. So like if I were doing this, I would use geometry. You're just, you've got a triangle, a square, a triangle. Add those up, those areas, and then you're subtracting that area. Or if you want to figure out the formulas for the lines based on the graph and just compute the antiderivative, you can. F prime of 2.5, remember the derivative of this is just lowercase f of x. So you'd be plugging in 2.5 and you can see that that value is equal to 1. So I don't know if it's helpful for you to see my quick remarks or not, but just like looking at this, I can tell f prime of 2.5 is going to be equal to 1. This is something you've seen before on one of my tests, optimization problem. And maybe it's even a little bit simpler than the one that you saw on the test. Like you've got this nice picture there for you. Look at the area of the inscribed rectangle, with corners on this curve, y equals 4 minus x squared. What else? Critical points. Oh yeah, something that came up on the most recent test. Critical points, that's places where the first derivative is equal to 0, and those can be maxima or minima or neither. Inflection points can occur when the second derivative is equal to 0, and the intervals of concavity are where the second derivative is positive, concave up, or the second derivative is negative, concave down. So inflection point would be where the second derivative is switching from positive to negative. So clearing that up from a test. There were multiple issues there, and that's separate from using the first derivative test or second derivative test to determine whether a critical point is a maximum or a minimum. So that's maybe a little topic I recommend all of you go study and review before. I won't ask about even functions. We haven't really talked about them in this class. And I also won't ask about curve sketching in this class. I don't do curve sketching anymore because there's really no reason for it. We have, programs that can do that for us. Will I post answers to this? No. I'm not going to be working all of these tests and spending hours writing down detailed solutions. So no, I'll post answers to the exams that I've given you, and I will not be posting answers to the practice final that I've just listed because I don't have them. This is just a courtesy to you that you can see it and look at it. But if you want to write down a solution to any thing that you've done on the practice exam, if you want to do the practice exam and send me your solutions, then I'll comment on them and correct any mistakes. But the value proposition of me just generically writing solutions out and posting them it seems like a lot of work for me, and it doesn't really seem to increase student grades, to be honest. So, but one-on-one correspondence where you're writing something down and I'm giving you feedback, that's actually really great. And I'm happy to spend as much time as it takes talking to you one-on-one about solutions that you've done. Net change in position, yeah, so just integrate the velocity. So moving left to right or right to left, that's just whether or not the velocity is negative. Evaluate the limits. Evaluate the intervals. So pretty straightforward stuff. And a nice little extra credit. And I don't want to talk about the extra credit in a review session. That's really, don't do extra credit unless you feel confident with everything that's come before, because it'll just be a waste of time. Extra credit in this context is not designed to boost a low score. It's designed like if you just want something extra to think about, like some extra challenge. So that's a little practice exam for you, and I hope it gives you like some stuff to practice. It gives you a sense about what to expect. It gives you a sense like culturally about like how the problems will be phrased and stuff like that. So hopefully that'll let your mind at ease. And if you would like to see me do any of these problems on the board right now, let me know and I'll do it. Or if you have any other questions, let me know and I'll turn it back over to you. Any extra questions? Anything else? There was a question coming in. Can I do problem 4 on this practice exam? Yeah, be happy to. And like everything else I do, there's this double-edged sword where not preparing in advance, hopefully I won't make too many mistakes or something like that. But let's see how it goes. So the problem says maximize the area of a rectangle lying above the x-axis and with its upper two corners lying on the curve y equals 4 minus x squared. So I'll redraw the picture here. So y equal to 4 minus x squared. And so this, when x is equal to 0, you're up here at 4, and then it looks like this would have roots at plus or minus 2, right? And so the idea being that you inscribe some rectangle. And by the way, how do you inscribe a rectangle? Like what I think you would do is you would look at this interval from -2 to 2, and you would pick some x value inside that interval. So see how I've just picked a random x value inside that interval, and what you would do is you would walk up to this point, which is x, 4 minus x squared, and then that determines for you the other point, which is going to have the same y value, but the x value will be reflected over. So this point would be -x, 4 minus x squared. So I think probably the secret to setting this up is also like understanding like the geometry of what's going on, like what are these 4 vertices. And so give the width and height of the largest rectangle and also its area. The interval of acceptable units for your objective function and the behavior of your objective function at the endpoints must be part of your solution for full credit. So this this language is not language that I'm using currently. But what the objective function is in this context is it's the thing that you want to minimize or maximize. In this case, maximize. So you're maximizing the area. So, and again, I wouldn't phrase it like this on your final. I wouldn't say objective function, but that is referring to the area function here. So you're maximizing the area and you're giving the width and height of that rectangle of largest area along with its area. And the last sentence is basically saying that we aren't just finding a critical point and solving for it, we're making some argument to show why the critical point actually is a maximum. So what we're trying to do is we're trying to write a function A for area, and let me make sure that the video is good, we can see this, we can hear me. Okay. So we're going to try to write down a function A in terms of x that represents the area, and we're going to maximize this function at the interval from -2 to 2. And so we know how to find the maximum of a function on a closed interval. That's called the extreme value theorem. The maximum can only occur at critical points or at endpoints. So what I'm going to need to do is differentiate this, set it to 0, find those critical points, and I'm also going to need to determine the area of this rectangle at those endpoints. And what you can see is that the area of a rectangle is base times height, and when you're at an endpoint, your height, your base would be equal to 4, but your height, the y value, would be 0. So in fact, these two endpoints have 0 area. And so that which is telling you that your maximum will in fact occur at a critical point. And you could say, well, gosh, Ken, like maybe you could move x bigger than 2. But at that point, you're no longer inscribing a rectangle. So I am using some context clues here. The picture was given to me that I really am, working in this part of the parabola, which is kind of like a reasonable thing to get from context, right? Like you're inscribing inside the parabola. Okay, so fine. So area is length times width. And actually, I'll just go ahead and call that L L times W, so L times W. And so what's my length? Well, I guess maybe I should call it like base times height. Doesn't really matter, base times height. So what's my base? That would be like this length, which is evidently 2 times x, because I have this distance, which is x, and that distance, which is x, right? So b minus a, that's x minus minus x, that's 2x. And what's the height? Height is just given to me by my y value, 4 minus x squared. So multiplying this out, I'm getting now 2x times 4 is 8x, and then minus 2x cubed. So 8x minus 2x cubed. And now I just go to work. So I know that I need to use the extreme value theorem to maximize this function on this interval. I know my endpoints are 0. Let's find those critical points. So this function, it's a nice polynomial function. It's straightforward to differentiate. So the derivative of 8 times x is 8. And the derivative of 2 times x cubed is 6x squared. And so if I set that equal to 0, this is going to give me that 8 is equal to 6 times x squared. Dividing both sides by 6 now gives me what 8 over 6 is equal to x squared. So that's what 4/3 is equal to x squared. And therefore 2√3 must be my x. And sure, plus or minus 2√3, but look at the picture, positive x and negative x. So when you are determining a rectangle to be inscribed, you're really only selecting x values that are between 0 and 2, and then the negative x is determined for you. So, I mean, if I were writing this down on an exam, I'd probably write down a sentence saying that we really only need the positive root here because of the way the problem is set up. Yeah, so question, where did the 2x and the 4 minus x squared come from? So that's because from the instructions, we are trying to find the area of the inscribed rectangle. The way that you make an inscribed rectangle is like you would start with a point on the x-axis, which I've labeled x. You'd come up here to this point x, 4 minus x squared, and then go on over and come down. So the area of this rectangle is the base times the height. And so the length of the base is 2 times x. And the height is nothing but the y value of this point. So the height is 4 minus x squared. Any other questions, comments before we go on? Okay, and so given that x is equal to 2/3 and that it's the only critical point, if a of x is, if a of, 2√3, if a of 2√3 is bigger than 0, then certainly it must be the maximum by the extreme value theorem. So I'll go ahead and, put that in. A of 2√3 would be, just plug that in here, 8 times 2 over √3, so 16 over √3 minus 2 times 2√3 cubed, so 2 cubed is 8, and √3 cubed, that's 3 to the 3/2. So I don't know. 16 over √3 minus 16 over 3 to the 3 halves. So let's put this over common denominator. So like this would be just 3 to the 1 half. So if I do like 3 cubed over 3 cubed, that's the right common denominator, right? So wouldn't this be 8 times 2 is 16 times 27 minus 16 all divided by oh yeah, I messed this up. So this is 3 to the 1 half, and then I would actually just want to do 3, right? 3 to the 1 to give me add together and get 3 to the 3 halves. So messed that up. So that should just be 3 over 3 for common denominator. So that's actually 16 times 3 minus 16 over 3 to the 3 halves, which is now 16 times 2, that's 32 over 3 to the 3 halves. So that's my answer for the area. And but whatever, I won't spend too much time just like doing arithmetic. Anyway, this is certainly a positive number, and therefore it is the maximum of the area on that interval. And we also need to find out the base and the height. So the base is 2x, and x was 2 root 3, so the base is 4 root 3, and the height would be 4 minus x squared. So the height would be 4 minus 2 root 3 squared. So the height would be 4 minus 4 thirds, which is what? 12 thirds minus 4? 8 thirds? So these are the dimensions of the base and height. And again, like my board work comes with verbal explanations, but if I'm doing this on an exam, I am going to put some writing there to explain what I'm doing. So, I'm going to be saying something like, by extreme value theorem, x equals 2 root 3 is a maximum. That's coming from the fact that there's only one critical point and both the endpoints evaluate to 0 for that area function. The other way you can prove this is a maximum is with the second derivative test. So you could actually calculate the second derivative here, end up with negative 12x. You'll see that the second derivative at that point is negative, and therefore the critical point must be a maximum. But you don't have to argue that way. There's different ways you can argue, either with the second derivative test or with this nice extreme value theorem, if you've got an interval that you're maximizing over, like we do in this case. Yeah, so I think problems like this, yeah, thanks for suggesting doing that. I think problems like this, even though every single particular step is not that difficult, the difficulty in problems like this are really setting it up, like making that mathematical model and then putting every single piece together to get your conclusion, and then of course remembering to show why your conclusion is true. So there are a lot of elements that go into these optimization problems. So I hope that gave some utility or some help. Anything else, either from previous final or from anything else in the course? Okay, so that's that's calculus for what it's worth, or at least my version of it in spring 2021. So I hope it was kind of I hope you got something out of it. I hope it was kind of interesting and engaging. If not, then I'll talk like Puck and tell you to think that it was nothing but a Midsummer Night's Dream. Um, Got one more question coming in. What's the difference between dy dx and d over dx? Yeah. Question was, what's the difference between dy dx and d over dx? This refers to the operation of taking the derivative. This refers to the derivative of the function y. So if y is equal to f of x, dy dx is literally f prime of x, where this you would never see this written by itself. This refers to the operation of taking the derivative. So you would apply this to something. So if I did this, this would mean apply the operation of differentiation to the function y, and that will result in the quantity dy dx. So it's a little bit of a subtlety. So this represents a particular quantity, whereas this, they are equal together. They're the same thing. But when you write it like this, you're sort of indicating that you want to differentiate this quantity, and then that's what it's equal to. So it's really just notational. You see people use different versions depending on their mood or what they're talking about, but they mean exactly the same thing. And you should never see d dx by itself. It should always be applied to something. I'll hold one more minute. Any more questions? And maybe to give you like a real world example of that is like you could write d dx of, like if you did something like that where this wasn't called y, right? You just stuck in a polynomial there. Then you would say this is, 2x plus 1. So like one reason you might use this notation instead of that is if the thing you're differentiating wasn't called y, if you just wanted to stick in an expression there, then you could use that notational setup. Okay, if there's nothing else, then I hope you all have um, a wonderful day or a wonderful night, as the case may be. And try not to get too stressed out. We're so close to the end, and we'll see you back here for the final exam at 12 p.m. Great Barrington time on Friday, 2 days from now. So thank you everybody for your time and attention. Have a great day. Have a great summer. Wish you all the best. Keep in touch.